speaker is Manuel Baumann from KIT in Germany, and he will give us an overview into sustainability perspectives of energy storage technologies. So, Manuel, thank you.
Thank you very much. Yeah, thank you very much, Miriam. It's a pleasure to be here today. And I'm going to talk, as announced, about the sustainability perspective. And to be honest, I did not know what to present, so I literally prepared everything. That's why I have plenty of slides. However, we can adjust and we can skip some slides because I think a lot has been already shown. So I'm going to talk about, challenges, methods, and prospects of sustainability assessment. And the goal will be to provide you an overview of how to carry out a sustainability assessment for energy storage technologies and provide you some examples for the operationalization of the same. The agenda, well, challenges, sustainability assessments, methods, indicators, use cases, and conclusions at the end. So as an introduction, is there a common definition of sustainability? Where there is, somehow, based on the United Nations Brundtland Commission, which defined that sustainability is, well, meeting the needs of the present without compromising the ability of future generations to meet their own needs. So we have to act in a way that we can assure that our children and the children of our children will be able to live in a better or a comparable way like we do nowadays. And now a question into the round, because there are a lot of smart people here. And I ask you, with this definition, what do you think will be relevant in terms of sustainability related to the energy transition and energy storage? Are there any indicators, criteria, aspects that fall into your mind when you talk about sustainability? Don't be shy, otherwise I will pick somebody. I will pick Koroush. So? Climate neutral, yes, very important. Another one? Okay, Laura? Acceptance, yes, so we have the social acceptance, so we have climate change, social acceptance. These are some examples, true. And mentioning climate neutrality, and it has been mentioned quite often, the 1.5 degree Celsius goal. Do you think that this goal is reachable with our policies and attempts that we're having on the street at the moment? So who thinks it's possible? Just raise your hand. Oh, this is the least optimistic auditory I had for a long time. Okay, so let's check it. There is something called the carbon clock, and here you can see how many years remain to achieve the 1.5 degrees Celsius goal. What they do is they have a carbon contingent that can be used, defined on the goals of the IPCC, and there we can see that we have 6 years remaining to convert all the measures that we have to achieve the 1.5 degrees Celsius goal. But this has been shown, we already surpassed the 1 degree border, and if we look at this thermometer, which is a global mean temperature increase is shown there, and it's the climate action tracker, we can see that with the policies and actions that we have nowadays, we will not be able to achieve the 1.5 degrees Celsius goal. Rather, we will be heading towards 2.7, 3.7, 3.6 degrees Celsius. Even with the most optimistic scenario here, we will be somewhere about 1.8 degrees Celsius. So this is just to show that we're not talking about something that will happen in 20 years. We have to act within the next 6, 7, 8 years. So there is some urgency here. And also, if we talk about sustainability, it's not about only the energy system. We have to think in intertwined dimensions. So we have technology, which is embedded in the energy system. The energy system itself is embedded in society, and the society is embedded in environment. Yes? Without environment, without nature, there would be no society, and there would be no energy system and no technology. And we already talked about climate change. we will not, or we do not know how it will look like in 20 years. Will there be 1.5 degrees Celsius or 6 degrees Celsius of temperature rise? So another factor is the geopolitical context. It's also changing. That means we do not know how value chains will change in the future. So will there be a difference, a bigger difference between the north and the south part of our planet? Will there be new conflicts? How will resources, how will these value chains look like in the future? And also the distribution of money, will it change in the future? Will China, for example, overtake in economic terms the US and Europe, yes? So that we might not even be the most technological developed producers in the world anymore. What kind of new technologies will be there? Reactive metals, new materials for battery storage, materials acceleration platforms. So there are a lot of factors that can influence this interrelationship. Societal context, ethical questions, what are fair energy prices, etc. These are all aspects that downfall into sustainability. And of course, how will the energy system of the future look like? How will markets develop? Flexibilities? Will there be sector coupling? Long-term storage? Is there a solution available? And how will this different fields, how will they relate to each other? So from this we can derive some insights. We can say that the relationship of environment, technology and society is dynamically changing over time. That means that our notion about sustainability is something that has only a temporal validity. And what is essentially is to know the boundary conditions of socially desirable embedding of innovative technologies in a sustainable way. From this results that there is also no best sustainable technological solution. Yes? There is nothing like that. Why? Because the problem is changing. That means if we talk about sustainability, there is the need to define goals and to have a scale of improvement. And it's a kind of iterative process that we have to consider. And there are some developments. I mean, we have climate change, we talk about that. We have something called the Sustainable Development Goals that give us a frame of goals, what we should achieve in the future. We have a European Green Deal, a new Circular Economy Action Plan, etc. All these things have been presented before. And there's always this guy that says, well, what if it's a big hoax and we create a better world for nothing? Well, I mean, at least we're doing something that improves our quality of life. So it's ridiculous to state that climate change might be a hoax or something like that. But unfortunately, this is the truth. However, there are several sustainability concepts that can be taken into account if we want to achieve a more sustainable energy system and more sustainable energy storage technologies. One of those is the integrative concept of sustainable development called ICUS from the Helmholtz Association. Then you have the more famous Sustainable Development Goals, which are 17 goals with about, I think, 170 sub-goals. So it's a broad set of criteria and it covers, well, a lot of different aspects, like, for example, water, then you have affordable energy, etc. So different goals stated here. It's in German. That was why I was struggling in the translation. And we have the triple bottom line model of sustainability, which actually consists of the planet, people, and prosperity. And this one is the model that is applied the most in sustainability assessment because it's quite easy for operationalization. If we talk about sustainability assessment, we face a problem, which is called the Collingridge dilemma. At the beginning of the development of a technology, yes, so you might take TRLs or whatever you want, we have a high potential for sustainable design if we start with material selection, lab scale prototype, until we get to market diffusion, where the potential gets lower. However, this potential for sustainable design is accompanied by this Collingridge dilemma, which says, well, on the one hand, we have a power problem. So opportunities to steer are plentiful in early technology development stages, but hard to choose from. While at later stages, this is reversed. So this is somehow in line with this. On the other hand, we have an information problem because we cannot easily predict impacts until the technology is developed and when it enters market. So this is a problem. We have here the power, but the lack of information. And at the end, it's the other way around. And if we look at sustainability, you can imagine that it is a complex problem. It's a so-called wicked problem. What does that mean? It's a type of problem which is ill-formulated, where the information is confusing. There are many clients and decision makers with conflicting values, and the ramifications of the whole system are thoroughly confusing. So if we look at a wicked problem, we have a lot of stakeholders that cannot agree. We require complex judgment. We have no clear stopping rules, no objective measures of success. And if we start to look at the problem, we might find new problems and have to restart the process. That means we need frameworks that allow us to have an iterative approach to the sustainability sphere, considering also multiple actors. That means for sustainability assessment, we need, operationalization of sustainability. And to do so, we have to downscale the problem and adopt to the object of consideration, in our case, energy storage. And of course, we also need to take into context the type of questions and assessment needs. And here, a concept comes into play, which is the life cycle-based sustainability assessment. Because any environmental, economic, or social assessment needs to take into account the entire life cycle of a product. That means we have to, if we look at a certain product as energy storage, to consider natural resources, the extraction of the same, production, use, maintenance, disposal, and recycling of a product. Yes, only considering all these life cycle stages, we will be able to conduct a sustainability assessment. And for this, we have certain indicators available. Some of them have been named: acceptance, global warming potential, local added value, life cycle cost, and so on and so forth. So there is a wide set of different indicators. In the SDGs, about 170. So it's quite hard to look at all of them. And we have a toolkit where we can try to quantify all these different indicators by using surveys, life cycle costing, input-output analysis, and so on and so forth. But when we select the methods, we have to be very careful. Why? Because they always depend on the project context, and there is only a limited amount of time and money available. That means we have to consider this and also to look at the availability of data and the expertise of the people involved. And robust data is required, because if we do not have sufficient data, this will happen. Rubbish in, rubbish out. This happened to me actually when I was in thermodynamics during my studying time, and I had to model, I think, in the engineering equation system, a power plant, and obviously I did something very wrong. Okay, so this means that sustainability assessment is not a straightforward process. You start with, you start with the problem, you identify it, you structure it, you try to operationalize it and apply and test the approach, but all these steps are in an iterative way. That means you might have to adjust it from time to time and restart. But that is, I think, the case for most modeling approaches anyhow. So to make here some dissemination within the Stories project, we looked at several sustainability assessment methods, and we provide input papers where we summarize all these different methods for the sustainability assessment of energy storage technologies, where we provide a rough guideline to use all these methods. So if you want to start with something related to sustainability assessment, you can take a look at it soon, hopefully. I think now coming to the specific example of energy storage, I don't know if I have to start and tell you this again. You can separate storage technologies based on their discharge duration, the form of energy stored, or on the system level integration, which is central or decentral. This was presented, so I will not go into that again. We have different forms of energy storage, and we have important indicators for energy storage, which are energy density, power density, efficiency, safety, etc., sustainability aspects, and many more. But the challenge is that you will not have a perfect energy storage solution. There is always a trade-off. That means you will not be able to have low-cost technology with high environmental standards, and so on and so forth. So you have always a trade-off. For example, short-term storage, you can provide a high amount of power within seconds, and for midterm or long-term storage, you can provide a lower power over a longer time, as an example. Seconds up to hours. And energy storage is able to cover several application fields. This has been shown before. I will not go into detail. But a difference is that, for example, for power quality regulation, you might have the same criteria as for the other application fields, but the priorities are different. So you have to consider that when you want to apply a storage technology. And also, you can integrate storage technologies on all these different levels, yes, starting from the distribution level up to the generation level. However, this has been shown before. And if we go into the sustainability assessment of storage technologies, we have to consider different application fields. Because if we have different technologies, 1, 2, 3, N, we have different technologies with different properties, which might differentiate in investment cost, global warming potential, etc. And we have an application field where we require a certain amount of cycles per day, a certain response time, which we have to match with the properties of the storage technologies to be able to have a useful benchmarking system or somehow a quantification of the sustainability of a storage system. And here the question is, of course, which criteria we have to consider. But if we come to hybrid energy storage, if we look at different storage technologies, it's like comparable to the graph that Kurush has shown. You have your storage time and the power rating and different technologies. But if we start to hybridize energy storage technologies, we might be able to cover a wide field of applications, as you see here. And that is the benefit of hybrid storage technologies. Also, if you look at the cost side and the stacking of services, so hybridizing a storage system and putting together all these benefits of storage that it might provide shows you that via the combination of different technologies, you might generate a higher benefit in comparison to a storage system that is, for example, only a lithium-ion battery. Okay. But now I'll come to some examples, which are storage technologies, in particular batteries. And there are a lot of battery storage technologies available. I will not go into detail, but you could provide a lot of use cases here. But I will just focus on 2. And I decided to show this slide. Batteries, a hot topic, because Stefano also said that at the starting time he was disappointed about all the promises that have been done related to battery storage. And there was a person that said a while ago, just as soon as a man gets working on the secondary battery, it brings out his latent capacity for lying. Scientifically, storage is all right, but commercially, as absolute a failure as one can imagine. Does anybody know who said that? It was Thomas Edison. Yeah, on the 2nd February 1883. But times change, you know, temporary validity of sustainability. 25 years later, the same man said, inside of 15 years, the entire vehicle traction in large cities in the United States will be done electrically. And I'm now manufacturing the battery that will permit this to be brought out about commercially, the Edison battery. He failed. Yeah, it's quite interesting. So same story 100 years ago. However, coming to batteries, and I have to speed up, I'm going to mainly talk about lithium-ion batteries, and there is not the lithium-ion battery. There are different chemistries available, all with different properties. I will not enter into that in detail, but you can say that the lithium-ion batteries does not seem to be at the end, so there are always new values being named, most recently from CATL. They announced that they have a 500 watt-hour per kilogram energy density battery, which would be a game changer, but let's see. In general, the lithium-ion battery is really a disruptive technology because, I mean, without lithium-ion batteries, we would have these phones, right? Or we would have this kind of electric vehicles with a battery in the back, or we would have this type of laptops with the battery attached to it. So the lithium-ion battery really has an impact on all the parts of our life, starting from a watt-hour level to a megawatt-hour level. So you all know from ancient times on the mobile phone, you could exchange your battery pack. It's not possible anymore. Up to the stationary storage that you can see here, and we'll focus on that. Some examples, I mean, this has been shown. This is how, in general, a storage system is built up. You have some cells which are combined to a module, to a rack, and then you can combine them into a system, which is here a typical container system. Other examples, here you have a storage container system, another one integrated in a building, here hidden as a garden house, very important for acceptability, and from the inside. And then you have, of course, these massive ones. This one has been named Moss Landing. It might also be extended to 500 megawatt and 6,000 megawatt hour storage capacity. So it's massive. And there are a lot of gigafactories that will come in the future in Europe to produce lithium-ion batteries. But this is actually, I stole this from a colleague, but it's great from Marcel. Present lithium-ion batteries are not fully sustainable, you could argue. Why? They rely on critical or vulnerable raw materials like copper, cobalt, lithium, nickel, etc. And mining has social impacts. You have, of course, the production, which is associated to cost, environmental and social impacts of production, technical performance needs some improvement, present recycling, etc., etc. But that applies for all technologies, yes? So there are issues with any technology. Well, some might be bigger, some might be smaller. And lithium-ion batteries will have a certain impact because this is a prediction from 2020, million metric tons of material required for lithium-ion batteries. Until 2030, you can see that there will be a high growth of the demand for some materials. For example, here, manganese or cobalt, and you see here the factors, how it will increase. And to give you an example about cobalt and lithium, you can see that it is a critical material, and also vanadium, by the way, is not due to abundancy, but due to the limits of production, because it's a co-product and it's mainly delivered from China. And you see that most of these materials are red. However, I will not enter into detail. Let's take cobalt and lithium as an example. Lithium is, cobalt is distributed mainly in the Democratic Republic of Congo, most of you know it, which poses a problem. But the amount of cobalt is being reduced in lithium-ion batteries for automotive applications. I would say the most cobalt is used still in your mobile phone, for example. However, this is lithium, also distributed different sources. Most of the people think that Chile has, or is the biggest provider of lithium globally, but it's Australia, not using lithium carbonate, but extracting lithium from spodumene, which is a different type. However, you can see here the distribution. Also, you can see, depending on the source of the materials, that you have social hotspots for battery material supply. So the mining and the preparation of the materials might pose some challenges. However, that's why we try to develop post-lithium-ion technologies based on abundant materials. And here, sodium-ion batteries are considered as one of the most promising technology. There are several companies that announced that they will enter into markets. For example, CATL, here again CATL for mobility and also for stationary applications. And there are only few studies available about the sustainability of the same. And just to give you an impression about the progress in the field, I had a podcast that I gave in January. I was asked in German about how does the future of sodium-ion batteries look like out of the sustainability perspective. And what I said was, yeah, well, let's see, I don't know where it will be used, but I think mainly in the stationary applications, because they first have to prove that the energy density will be high enough that it can be applied for automotive applications. Then 2 weeks later, it was Hina that announced that they will, or that they introduce now an electric vehicle based on sodium-ion batteries. So my podcast was obsolete. It did not get published, and it will not get published, hopefully, because it's already based on outdated information. However, the main arguments for environmental or sustainable Advantages of sodium-ion batteries are environmental aspects and costs. But not all of you are familiar with sodium-ion batteries, I guess. What's the difference? Sodium-ion batteries are actually based on the same principles like lithium-ion batteries, but they use aluminum instead of copper for the current collector, sodium instead of lithium for the cathode active material and electrolyte salt, and the use of cobalt-free cathode materials that you can also do with lithium-ion batteries actually, but it's always named. Yeah, so I have put it there. I will put it away in the next presentation that I will make. So lithium-ion batteries and sodium-ion batteries are same, but different somehow. The anode materials are different, and also the materials that you can use for the cathode side can vary. So here I showed you this. This is the challenge that we have, and what do we do? How do we compare a sodium-ion battery, which has a lower TRL, and benchmark it against a battery cell that has a higher TRL, that has already foregone a higher learning curve. Yeah, that's a challenge. To do so, we have to look on the technology readiness levels. So we start from basic principles, electrochemical investigation, cell component production and testing, development of semi-industrial production, and proven cell for commercialization, and how to compare. There are questions like which method should I use for my assessment, where to start, how to compare, how's the data availability, who's my target group. And for this you can, well, consider different methods which are very uncertain at the beginning, and they have a low interaction with society as they're not on the market. But I will skip that due to time reasons. So here are two use cases that I want to present to you. You see here the value chains, the value chain for a battery cell, starting from the material level, electrode level, cell level, module level, system level, application level, and end of life. And here we will look at a material screening use case. We will skip the cell production use case, and we will look on a cell recycling level and skip the battery system level. So here, use case number one, it's a material screening. It is a use case for technology readiness level below 6, yes? And we want to benchmark this low TRL system against a market established system, so lithium-ion batteries. You can find the results and the details here in this paper, and the scope of the assessment was only the material level and the electrode levels here, the electrode level, and we ignored completely this other aspects, yes? So, what did we do? We screened 42 cathode active materials, and we used 3 simple indicators: cost, carbon footprint, and criticality. Why did we use these simple indicators? Because we are working with a high uncertainty, and we do not have a lot of robust data regarding the performance of the cathodes. So that's why we said, okay, the indicators have to be simple, also simple to understand, because we were working together with our technology developers, 7 people, and we had a lot of workshops to discuss which type of indicators we should use. We used theoretical data from literature and electrochemical calculations, and this is how the model looks. So what we did is to collect the data for 8 lithium-ion cathode types and 42 sodium-ion battery cathode types. And then we looked on a raw material level and precursor level, and we used some stoichiometric calculus to look at the criticality, cost, and carbon footprint, and to provide a first indication about the sustainability of the different chemistries. And this was done in a simple way: traffic light system. Why? Because the uncertainty was so high that it would be wrong to say, well, the value is 1.0456 something. So. And we separated the cathode materials into acidic materials, which is, for example, NMC 622, which was the benchmark, and polyanionic materials, where lithium iron phosphate was the benchmark. So let's jump into the results. The first one was conducted for carbon footprint, so that means the global warming potential in kilogram CO2 per kilowatt hour of storage capacity. And here you can see the results, and it's a lot of results. But what you can see is directly, this is the NMC benchmark, and this is the LFP benchmark, and encircled the lithium-ion batteries in red, and below all the sodium-ion battery cathode types. And you can see that at least for the oxidic materials, they perform quite well, whilst for the polyanionic variants, you see that, yeah, they are also performing better or worse, depending on the chemistry. But more interestingly, you see here the different materials that are used in the cathode. And there are some drivers. Cobalt, nickel, and vanadium are the key drivers for the carbon footprint. Also, the energy density is very important, and surprisingly, we have a good correlation between the carbon footprint, costs, and criticality, but we have a very high uncertainty. So let's come to the cost, where we looked at the euros per kilowatt hour of active materials, and here you can see again, same structure of the graph, how the results look like. Here we did some Monte Carlo simulation. However, we could see that here sodium-ion batteries offer also potentially significant advantages. Right, but high uncertainties. And there's also a lot of sensitivity calculus here, which I will not present here. Then we looked at the criticality. What is criticality? Criticality is not one indicator, it's rather a term. And criticality consists of different indicators. One is supply risk, which you can see as a composite indicator that is based on several aspects, as for example, economic importance of a material, the amount of the recycled material that you can get, etc. And we used this for the European Union. And here you can see again in the same structure that the sodium-ion batteries performed quite well, but there is a high uncertainty. Then we had a discussion after presenting these three different types of results with our technology developers. And they were like, okay, so what do you recommend us? What shall we do? Which type of chemistry shall we prioritize? And then we said, okay, what we can do is to give you an indicative ranking. And that's what we did with a very easy method. And I don't want to look at Laura because it was the weighted sum method. And it's a very easy method. However, by doing so, we could provide a ranking. And here you can see that the group of Prussian blue analogs and silicate or sulfate-based cathode active materials were ranked quite well and performed quite well in relation to sodium-ion batteries. However, also doing some sensitivity analysis showed that the results are quite robust. So showing this result is an example that also in early technology readiness levels, on a lab scale, sustainability assessment can provide some guidance, yes, but with high uncertainty. And to be honest, at the beginning we said we want to use easy indicators. We want to do this very fast. It took us over 1 year to conduct this. So having in mind that what Kurush said, material acceleration platforms, where you have a higher throughput factor 10, would impose also that we have to be faster with our assessments, or they are coupled and integrated directly. However, so high uncertainty, that's what I said. Let's come to the next use case, a prospective LCA of sodium-ion batteries, a life cycle assessment of sodium-ion batteries. You can find the details in this publication, and here, looking at the value chain of the batteries, we looked here on the production and the recycling. So what we did is to look at the environmental impacts, which are for sodium-ion batteries, as I said. We used a life cycle assessment as a method and looked at the manufacturing, use phase, end of life phase, and the impact categories that we considered are global warming potential, so the kilogram CO2 equivalents per kilowatt hour, and the abiotic resource depletion, which is an indicator which describes the use of non-fossil resources, so in this case, metallic ones. And here you see the results for the sodium-ion batteries and the lithium-ion battery benchmarks for the global warming potential. So the kilogram CO2 equivalents per kilowatt hour with the different components and their contribution to the impacts. However, this is not important. What is more important is, surprisingly, because you can remember, everybody thinks that sodium-ion batteries might be more environmentally friendly. They have a higher impact than the lithium-ion batteries here. But if we switch the indicator from the global warming potential to the abiotic resource depletion, the picture changes completely. Why? Because we use here more abundant materials. So how do we compare this? Global warming potential looks not so good for some chemistries, but on the next slide, we see here that the chemistries here, for example, this one, the Prussian blue derivative, performs quite well. Yes. So what do we say to the technology developers? Is this technology now useful or not? Well, it's always a delicate discussion. However, if we consider recycling, so using the materials again for the battery production, you can go through several paths. I will not enter into detail here, but we also thought about this aspect and we integrated this to the modeling of the cells. So here you can see again the results for the global warming potential, so the kilogram CO2 equivalents per kilowatt hour. And you see here the sodium-ion batteries and the lithium-ion batteries. These are the results that I showed you before for the production. Here we have mechanical recycling, and here we have hydrometallurgical recycling and the net impacts. Now what is interesting is that you can see that recycling reduces the overall impacts for lithium-ion batteries in general, but for the materials that use abundant resources, you can see that the recycling, the deep recycling would even cause a higher environmental impact. Why? Because we have to invest more energy to extract the materials again and to put them back into production, and it would maybe make more sense to mine them again. However, this is based on modeling, so it has to be proven. And we did the same job for the abiotic resource depletion, and the picture looks, as shown before, for the production a little bit different. Here, sodium-ion batteries are quite competitive. Why is that? If we look at the different different cathodes and the materials that are contained here, you also see economic value attributed to these. Also, out of a recycling company business case, you would see that here the material value is higher, so it's more worth recycling this type of batteries than a battery that has a material value of $4 US per kilowatt hour. So let's come to an end for this part, and I'm still in time, perfect. What are the challenges and the transferability to other energy storage technologies? So if we look on a material level, we can say that the results are just valid for a certain material, and they can be very different on a component system level. Manufacturing, there's a high uncertainty when we look at emerging technologies, because we always have to consider an upscaling, which I did not show here. But the upscaling is an own task, yes? We assumed here same energy uses as for the lithium-ion battery production, which has to be proven first. Performance, considering lifetime, for example, for sodium-ion batteries in operation. I mean, you can do that on a lab scale, but will it be like that under, in real world conditions? We can't say, so we made assumptions here. Recycling. The recycling can lead to a completely different picture. Abundant materials are not necessarily the most sustainable direction. Primary sourcing might be preferable, but it has to be proven. Also, result interpretation, it has to be carried out very carefully, because depending on what you assume and what you want to show, you will be able to do so. So it's also a question of transparency. But we are not at the end, because there is still a challenge. I showed you the different use cases for ecology and the impacts here. I still have 5 minutes, right? Yeah, okay, I'll manage. And we have to consider here different stakeholders, different application fields, and this conflict of importance of different criteria. And here you can use MCDA for multi-criteria decision making to support your decision process. And what is that? That are mathematical procedures that can help you to look at a decision process and to make it very transparent by the use of weighting of criteria as one key aspect. And there are several methods available that can help you here, but there is no method that is a kind of great decision-making machine. That is not there. But this type of methods can really help you to understand the type of problem. There are several publications that you can look at from this branch of methods. Some of them are here, but what can be said. You see here a literature review for different storage technologies that was conducted with a ranking, so for different use cases. And what you can directly see that none of the rankings is comparable. That means that also this type of studies depends very strongly on the context. So here is one that we did. We compared it to the literature and completely different. To come to an end, the takeaways. Sustainability assessment requires a high degree of interdisciplinary work, for sure. Selection from a variety of possible indicators is always a challenge, and it's an iterative process. You need a framework for data assumptions because they can influence the results. And, well, sustainability analysis can really make a valuable contribution to technology development. I think that's key message and should be considered. And what shapes our sustainable energy future? We cannot predict the future, but we can shape it, yes? And that's why sustainability assessment is very important. Thank you. Questions?